Okay, what I've written on the board in lab, just telling people various things. Um, Found that people were unable to calculate, average accelerations, they're uniform accelerations, given the time and the displacement. Um, so I suggested you go back to this picture, which is pretty fundamental. This one's even more fundamental. This picture applies when the initial velocity is zero and the acceleration is uniform, meaning that the velocity changes at a constant rate. In that case, we know that your average velocity will occur at the midpoint, and your final velocity will be double your average velocity just by the geometry of these triangles. You got a triangle right here, similar to this triangle, with a 2-to-1 ratio between their widths, let's say, or between their hypotenuses. So there's a 2-to-1 ratio between their altitudes. Okay, well, we get A equals delta V over delta T because that's what. I better write a delta here. Acceleration is the average acceleration is the average rate of change of velocity. That's your most fundamental definition, maybe. And I'm not even going to write that down, but if that is echoing in your mind, you'd better write it down and make sure you understand it, because it comes up again and again. And the whole idea of one thing being a rate of change of another is really, really arguably one of the 2 or 3 most important mathematical concepts at, at this level, at least. Okay, well, anyhow, you have acceleration is this. In this case, the delta V, the delta T is from here to here, and the delta V is from here to here. Okay, so the delta T is just equal to whatever T is at this point. So we get velocity equals acceleration times time. Now that seems to be the label of this picture, but that's this. Okay. Reason that's this is because this is the rise divided by the run of this graph, which is the slope of this graph. And the slope of a linear graph, or the equation of a linear graph of a given slope that goes through the origin is just V equals slope times T. Again, it would be like Y equals MX, but it's slope times whatever your variable is here. And again, that's fundamental knowledge. You really need to understand that deeply and forever. Okay. In the case where your initial velocity is not zero, well, your picture looks like this. And I'm not going to decode the picture very much, but you have your initial velocity, your final velocity, and your average velocity is again at the midpoint. And it's equal to sum of the initial and final velocity divided by 2. That's how you average 2 quantities. If the acceleration is uniform, then there's your graph. And you have a change in velocity, VF minus V naught. Okay, that's this. So what do we have? Acceleration is the average rate of change of velocity, which is change in velocity over change in time, VF minus V naught over T in this case. So that your delta S, which is equal to the average velocity times delta T, is V naught plus VF over 2 delta T. Now that follows from this. And from these 2 equations that you get from this picture, you can derive all the other equations of uniformly accelerated motion. In particular, let's look at this one. You just take this equation and solve for T and plug it in here. You've eliminated T, and you've got this famous equation, which is going to lead us to the work energy theorem shortly. Okay. Now, if you go to the calculus of it, acceleration is the instantaneous rate of change of velocity. So if V is your velocity function, your acceleration function is dv dt, which means that your velocity function is an integral of your acceleration with respect to t. When you integrate this, you get at plus a constant. Constant is arbitrary, but regarding v as a function of t, then v of 0 would equal a times 0 plus the constant. So that the constant is identified with the velocity at time t equals 0. And we typically call that v sub 0. Okay. Now, v sub 0 doesn't necessarily always, for all authors and in all contexts, doesn't always mean the velocity at t equals 0. So you want to be a little careful about that. But that's the way we'll use it for right now. Okay, well then, since velocity is the rate of change of position, the velocities, instantaneous velocity is the derivative of the position function. Okay. So that the position function is an integral of your velocity with respect to t. Your velocity is at plus b naught. I use the v sub 0 instead of v of 0. We integrate that, and we get this equal to 1/2 at squared plus v naught t plus an integration constant. And we'll call the integration constant x sub 0, which is the position at time t equals 0. We have these two equations, which can also be combined to get two more equations. And in every case, we get a set of, but in the case I like, okay, it's not exactly so in your textbook. But as I've stated the equations of motion, which are totally equivalent to what's in your textbook, but slight difference. The slight difference is I use x minus x naught as s. Okay. So, or as delta s. Sometimes I'll call it delta s. It's the same no matter what I call it. The equations, as I phrase them, each have three variables, three parameters. There are five parameters that we talk about with uniformly accelerated motion: initial velocity, final velocity, acceleration, the time, and where is it? It's in here somewhere. Initial velocity, final velocity, acceleration, displacement, and time. All those very obvious. Been a long lab, I'm sorry. Okay. You get four equations, each with three unknowns. Four equations, each with three unknowns. Any uniform acceleration situation in which you know three of the five parameters, you can find an equation with those three parameters in them and one more. You know, I might have misstated. Let me say it again. It's a long lab. There are four equations, each with four parameters. Okay, four unknowns. Of the five are initial velocity, final velocity, acceleration, displacement, and time. If you know any three of those, you can find an equation with those three and solve for the fourth, because there are four variables in each equation. Once you've solved for the fourth, you know four of the variables, you can plug them into any equation that contains the parameter that you haven't found at that point, and you have a complete solution. You have all five parameters. You've completely defined the motion. Okay. Now, let's take this equation. Plug acceleration equals net force over mass, Newton's second law. I mean, F net equals ma, so A equals F net over m. Replace the acceleration by F net over m in this equation and solve for F net delta S. We did this in class. If you've forgotten it, if you've lost track of it, if you're not thinking of it as you think through these problems, you need to, at every opportunity, think back to these fundamentals. There isn't that much. Okay. Anyhow, you get F net delta S equals change in kinetic energy. Now, I assume you know the kinetic energy is 1/2 mv squared. You can do the work here and see that you get F delta S is going to be 1/2 mvf squared minus 1/2 mv naught squared. So I haven't defined kinetic energy. Actually, I have defined it. It's what you get when you multiply F net by delta S. Okay, change in kinetic energy. is what you get when you multiply out net by delta S. And it turns out that the expression for kinetic energy is 1/2 mv squared. That's the work energy theorem. Then we can expand the work energy theorem to the conservation of energy. And we define conservative forces as forces, and I haven't written down the definition. You should know the definition. Definition of conservative force is one that's path independent. So I guess I will write path independent. If you put energy into, if you, well, I'm not going to come up with the right phrasing, so I'm not going to say what I was about to say. But this is a path independent force. This is non-conservative. It's not path independent. Typical examples: gravity. You lift something up and you release it. You get the work. You get a kinetic energy when it falls to the original position. You have a kinetic energy that's equal to the work that you used to lift it, less a little bit of energy loss due to air resistance, because you don't want to go doing this in a vacuum, you'll explode. Okay. That's an example of a conservative force where we put work into, we do work against conservative force and we release it, we get the energy back. FNC would be like the air resistance, okay? I mean, there's air resistance when I lift it. If I drop it, there's air resistance. The air resistance is not the same on both paths. Even if I lift it slowly and lower it at the same speed, the air resistance is in that direction when I'm lowering it and in this direction when I'm raising it. Friction, if I slide something across the tabletop, I slide it over there and back here. Friction does work in this direction when I'm sliding it in this direction. And when I come back, it's doing work in that direction. It's exerting force in that direction. So the frictional force is not path independent. Gravity exerts the same force on that block wherever I move it. It's path independent. Spring forces are path independent if you have an ideal spring. Okay. So net force then can be broken into conservative and non-conservative, at least in principle, can be broken into a conservative component and a non-conservative component. So that the work done by the net force, which is what you get when you multiply the net force by your displacement, is equal to the work you do. It's the work done by the conservative force plus the work done by the non-conservative force. I was going to say the work you do against the conservative force, but that's not right. Okay. So work done by the net force is the work done by the conservative force plus the work done by the non-conservative force. The work done by the conservative force, by definition, is equal and opposite to the change in the potential energy. That is the definition I use for potential energy. It's equal and opposite. Change in potential energy is equal and opposite to the work done by the conservative force. So we have this, and we can put this into this form very easily. Just add delta U to both sides. And the work by the non-conservative force is a change in potential energy plus a change in kinetic energy. One result of that is if you have no non-conservative forces, then any change in potential energy is accompanied by an equal and opposite change in kinetic energy. So if there are no non-conservative forces involved, to increase the potential energy, you have to decrease the kinetic energy by an equal amount. Or to increase the kinetic energy, you decrease the potential energy. That one's easy to understand. You drop this piece of chalk and gravity does positive work on it, meaning that the change in potential energy is negative. So you have a negative change in potential energy accompanied by a positive change in kinetic energy. There were no significant non-conservative forces at work here. Now there is a little air resistance, but it's pretty negligible at the speeds this was moving. Okay, so there we have a structure that starts with a couple of simple diagrams or simple calculus definitions and leads to some equations of motion, one of which tells us at least for a constant mass and a constant net force, acceleration's net force over mass. Plug that in, we get all this. For spring, force spring is negative kx on an ideal spring. Okay, you pull the spring out, spring exerts a force in the opposite direction. So you're doing negative work on the spring. And the spring is also doing negative work on you because it's pulling in this direction and it's moving in this direction. Okay. You can think of the force exerted by the spring, which is negative, if x is positive. And of course, you could extend this graph back here so that if you compress the string so that x becomes negative, spring force increases. You can worry about that aspect of it. In this simple case, if the force you apply is equal and opposite to the force exerted by the spring, which pretty much has to be the case, then the applied force is kx. So you're doing work kx, spring is doing work negative kx. Turns out that the spring force is conservative. Spring exerts the same force whether you pull it this way or this way. At this point, it's the same force here as it is here. Okay. The work done by the spring is therefore on an interval from x1 to x2 between 2 points. And let's just go ahead and illustrate that. Here's x1 on this line, x equals x2 in this line. Without going into detail on the fundamental theorem and everything in areas, you know that the work done on an interval is the integral of the force over that interval. Okay, I hope we're clear on that. So you do this integral, and I just did the wrong, shaded the wrong region. Work done by the spring is down here, and it's negative. It's under the x-axis. Okay, work done by the spring is the integral from x1 to x2 of the force, negative kx dx. You do that integral, and you can do that integral. It's 1/2 kx squared, value at x2 and x1. It'll be the negative of 1/2 kx2 squared minus 1/2 kx1 squared. And that's equal to the, and equal and opposite to the change of potential energy of the spring. So the change of potential energy of the spring is 1/2 kx2 squared minus 1/2 kx1 squared. Potential energy of the spring. Then we generally say relative to the equilibrium position, it's 1/2 kx squared. Equilibrium position being the position at which the spring is exerting no force, but if it's pulled out a little, exerts a force, and if it's compressed a little, it exerts a little bit of force. Okay. Potential energy of gravity is your old MGH, which misleads people. It's been misleading physics students for millennia, I suppose. But H is your vertical position measured relative to some fixed point. I prefer to think of the change in gravitational potential energy as mg delta y. Okay, why is that? Gravity is exerting a force mg in this direction on this mass. If I lift this mass, I'm doing work against gravity, so gravity is doing negative work on the mass. Okay. So when delta y is positive, the work gravity does on the mass is negative mgy. So the change in potential energy is positive mg delta y, because again, the change in potential energy is equal and opposite to the work done by the conservative force. One way or another, that's energy. Now there's more. We of course have to know vectors, and we have to know things like triple acceleration equals v squared over r. Centrifugal force is mass times centrifugal acceleration, which is just m v squared over r. You don't really need both of these formulas. You just have to know that the centrifugal acceleration is v squared over r. And you ought to understand the derivation of that by shrinking isosceles triangle formed from velocity vectors, okay? It's done in your book. I think it's done in any decent textbook. You should really understand it so you don't misapply it. Recently, somebody tried to misapply it by using it to calculate the acceleration of a falling object. Okay, doesn't work. The units don't work, and the formula is irrelevant to that. Of course, somebody's remembering v squared over r. They weren't remembering centrifugal acceleration, and we were in a rotational situation where v squared was related to the potential energy, and r is the radius at which a certain mass rotates. And so it'd be a fairly natural error to make, but it's just an example of how you can pull out a formula that seems to have some relevance to the quantities you're looking at, but it doesn't tell you what you're looking for, okay? That's your centrifugal acceleration. The acceleration you need to keep things from going in a straight line when they're going around in a circle, okay? Now there's a lot about vectors, and you just have to know how to use vectors. We might review that somewhat because it's relevant, and free body diagrams. So you really want to think about vectors. In free body diagrams, there's a test coming up, and I really want to see more free body diagrams and better free body diagrams. I've seen some good ones, but for the most part, they aren't very good. Okay, they don't include all the forces, and that, and the fact that I'm still not seeing units in a lot of calculations. They're just kind of slapped on at the end. If you pull out a wrong formula, you're very likely to get wrong units. So if you're doing your unit calculations, sometimes you get really good feedback, aside from understanding the relationship of the quantities represented by the units, okay? So I stress units. I stress understanding this fairly simple structure. From motion through Newton's second law, through energy, through the conservation of energy and potential energy, okay? Understand that and try to think anything that you're doing back to these principles. You'll be much better at solving problems and much more likely to do well on the upcoming test.